Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, Blaise Pascal's treatise on the arithmetical triangle, published posthumously in 1662, stands as a foundational work in the history of mathematics. This essay undertakes a structured examination of Pascal's claims within this work, focusing on a detailed analysis of its sections. It seeks to unpack the underlying principles, assess the logical structure, and evaluate the enduring significance of Pascal's exploration of what is now commonly known as Pascal's triangle. Our intent is to offer a comprehensive elucidation of its internal architecture, providing professionals, historians, and serious students with a resource offering both detailed analysis and scholarly critical insight. Section 1: Definition of the arithmetical triangle and its generation. Pascal initiates his treatise with a careful definition of the arithmetical triangle. He describes it as a table of numbers, arranged in rows and columns, whose entries are generated according to a specific rule. Each number is the sum of the number above and to the left of it. Pascal is meticulous in laying out this generative process, emphasizing that the entire triangle springs from this single, recursive definition. He identifies two fundamental properties of this triangle: the property of being bounded by the first row and the first column, both comprised entirely of ones, and the aforementioned rule of formation. Pascal states clearly what it is. Pascal states what it is, instead of what it is not or what it contrasts to. He directly outlines the process by which the arithmetical triangle emerges from its conceptual starting point. The triangle's construction, Pascal insists, stems entirely from the repeated application of simple addition, a fact central to understanding its diverse properties. Pascal is careful to make evident this specific process. The significance of Pascal's initial definition lies in its operational clarity. Unlike many prior explorations of similar numerical arrangements, Pascal provides a transparent and unambiguous method for constructing the triangle. This explicitness allows for rigorous examination of its subsequent properties. Pascal's approach differs from earlier investigations that may have focused instead on observed patterns. Without a systematic construction, Pascal's articulation of the triangle highlights its inherent algebraic structure. Examining this section reveals that his framework establishes a foundation for studying combinatorial problems as well as aspects of probability theory. Section 2: Naming and numbering conventions within the triangle. Having defined the arithmetical triangle, Pascal proceeds to establish a precise system for naming and numbering its elements. He introduces the terms base, exponent, and cell to refer, respectively, to the row number, the column number, and the element at a specific row-column intersection. Pascal's terminology aims for clarity and precision. He proposes a structure where each element can be uniquely identified, facilitating the expression of mathematical relationships. It becomes clear how, in Pascal's framework, a general element with base b and exponent here is the cell with base b and exponent. The import of this section lies in its establishment for a robust notational system. Pascal recognizes the necessity of possessing terms which would describe and distinguish each of the triangle's elements. Without such a system, expressing and proving properties becomes cumbersome. The elegance with which Pascal formalizes these definitions shows that he is concerned with communicating mathematical ideas effectively. The precision in his terminology allows him to express the algebraic relationships within the triangle in a clear and concise manner, setting the stage for the subsequent proofs he presents. Pascal's careful approach emphasizes the importance of rigorous notation for mathematical clarity. Section 3: The first deduction: Equality of cells symmetric along the. Pascal presents a foundational theorem asserting that cells equidistant from the middle of any base are equal. In modern terms, this is the statement that the binomial coefficients possess symmetry. Pascal does not utilize modern notation. His demonstration of this property relies on the recursive generation of the triangle and the fact that each number is the sum of those numbers placed above to the left, that elements symmetrically positioned within a row assume equivalent values constitutes the first major observation the triangle possesses. Pascal provides a rigorous argument demonstrating the symmetry from the ground up. So this deduction is key precisely because it demonstrates that the arithmetical triangle embodies a specific kind of symmetry. The symmetry indicates that combinations of n objects taken k at a time is equivalent to combinations of n objects taken n minus k at a time. Pascal's argument, although presented geometrically, reveals the underlying algebraic relationship. It underscores that seemingly distinct combinations are in fact equivalent, reflecting the inherent structure of binomial coefficients. The theorem highlights combinatorial equivalence. Pascal reveals the fundamental property of the binomial coefficients. Section 4, the second deduction, the sum of cells in a column. Pascal then focuses on the second important property of the triangle, namely the claim that the sum of cells in any given column, from the first row to the base of any cell in that column, is equal to the cell in the next column situated at the base. The claim is expressed verbally. The algebraic equivalent would involve a summation of binomial coefficients. This deduction is vital in Pascal's analysis, revealing a relationship between columns, and this theorem is a concrete example of the additive properties that characterize the triangle. Such a property underscores the connection between adjacent columns. It offers a method for calculating sums of combinations, providing a practical technique for addressing combinatorial problems. That such a summation should equal adjacent elements indicates that the recursive definition of the triangle propagates through each of its dimensions. Pascal, with the theorem, enables a more efficient calculation of combinatorial sums. Section 5. The third deduction, figurative numbers. Pascal moves on to figurative numbers, integers that can be represented as regular geometric arrangements. He establishes that the cells in the arithmetical triangle correspond to various classes of figured numbers. For example, the third column contains triangular numbers, the fourth column contains pyramidal numbers, and so forth. Pascal's claim is that the arithmetical triangle provides a unified framework for understanding properties of figured numbers of all different classes. The relevance of this section lies in the historical context. Pascal's time witnessed significant interest in figured numbers. Showing that they are embedded within the arithmetical triangle provides a valuable result. It connects what might have been perceived as distinct branches of mathematics, uniting geometry, number theory, and combinatorics. Pascal's proof demonstrates that figured numbers are simply a special case of the more general structure of the arithmetical triangle. He connects these concepts. Section 6, solving the problem of points dividing stakes in an unfinished game. Pascal famously applies the arithmetical triangle to the problem of points, which concerns the equitable division of stakes in an unfinished game of chance. Pascal's proposition lies in the idea that a fair division must consider the probabilities of each player winning. These probabilities can be calculated using the arithmetical triangle. His claim is that the arithmetical triangle gives the solution to this long-discussed problem. He maintains that the triangle provides a rigorous and fair method for determining stakes. This section demonstrates the practical utility of the arithmetical triangle in addressing real-world problems. Pascal's approach goes beyond theoretical explorations. Pascal shows how the arithmetical triangle can be applied to questions of practical interest and relevance, the fair allocation of resources, when faced with uncertainty. His work on the problem of points laid the foundations for probability theory and statistical analysis. The result is foundational. Pascal demonstrates its utility. Section 7, applications to combinations and the doctrine of chances. Pascal elaborates on how the arithmetical triangle can be used to calculate combinations and understand the doctrine of chances. He demonstrates that the cells in the triangle directly correspond to the number of ways to choose a certain number of items from a larger set. He shows that the triangle illuminates the underlying structure of probability distributions. His claim is that understanding its properties allows one to address a wider array of probabilistic problems. This section emphasizes the triangle's applicability to combinatorial analysis and the calculus of probabilities. Pascal's exposition is not limited to the problem of points. Pascal connects the triangle to the broader landscape of probability and combinatorics. He shows how to solve combinatorial problems. Pascal explains how the arithmetical triangle serves as a powerful tool for analyzing random events and making predictions based on these events. Pascal shows how his result can address a spectrum of problems. Section 8. The use of the triangle in solving problems of chance with multiple players. Pascal extends his analysis to consider problems of chance involving multiple participants, demonstrating that the arithmetical triangle's fundamental principles prove also applicable to more complex scenarios. He makes this determination by illustrating how, even with more than two players, the probabilities of each participant's success or failure can be calculated with the help of the triangle. This section of his treatise shows how the arithmetical triangle's versatility extends beyond two-person games. It handles problems with more complex structures. This examination reveals the remarkable adaptability of the triangle to address even more sophisticated probability scenarios. This flexibility demonstrates its usefulness as a tool for analyzing probabilities. When multiple participants are involved, Pascal's approach enables analysis of probabilistic problems with many complex elements. In doing so, Pascal lays the groundwork for a wider understanding of probability across diverse contexts. Pascal elaborates on its applicability. Section 9. Generalization of the arithmetical triangle and its properties. Pascal delves into generalizing the arithmetical triangle, examining how its properties extend and adapt under various transformations and extensions. This section on the arithmetical triangle showcases Pascal's keen interest in exploring the robustness and adaptability of his discoveries. He suggests that the basic principles underlying the triangle are not limited to the specific configuration he initially presented, opening up avenues for further mathematical exploration. This generalization emphasizes Pascal's ingenuity and foresight by demonstrating that the concept of the arithmetical triangle can be expanded and modified while keeping its essential properties intact. Pascal invites future mathematicians to build upon his initial work. This adaptability makes it possible to apply similar principles to a range of problems. He is not limited by his starting point. Pascal's work is not constrained by its specific instantiation which he gives at the start of the essay. Section 10. Relationship to the binomial theorem. One implicit but undeniably important aspect of Pascal's work lies in its close relationship to the binomial theorem. Although Pascal does not explicitly state the binomial theorem in its modern algebraic form, his arithmetical triangle provides a powerful tool for computing binomial coefficients. Any reader would use the principles in the essay to calculate coefficient. The numbers that constitute the arithmetical triangle are precisely the coefficients appearing in the expansion of a binomial expression raised to a non-negative integer power. The connection to the binomial theorem is critical. This relationship reveals that the arithmetical triangle is not just a numerical curiosity, rather its structure is deeply interwoven with fundamental concepts in algebra. Pascal's work, while focusing on the triangle itself, implicitly touches upon the cornerstone of algebraic theory. It provides a method for computing quantities central to mathematical understanding. The triangle has an implicit connection to one of the most important ideas in modern algebra. Section 11. The use of combinatorial arguments in the proofs. Throughout on the arithmetical triangle, combinatorial arguments serve as a bedrock for Pascal's proofs. He leverages the concept of combinations, focusing on the number of ways of selecting items from a larger set to justify several properties of the triangle. Pascal's approach is not focused on abstract algebraic manipulations. He instead focuses on direct enumeration of these possibilities. This reliance on combinatorial reasoning underscores Pascal's deep understanding of discrete mathematics. Pascal is also committed to providing an accessible and intuitive approach to mathematical proofs. Rather than relying on formalism alone, Pascal illuminates the reasons for each property. Pascal ensures that his audience understands not only that the properties are true, but also the underlying mathematical reasons why this is so. Pascal's arguments showcase a specific kind of mathematical reasoning. Section 12, Contemporary Reception and Critique of the Work on the Arithmetical Triangle, being published posthumously, met with a unique reception. However, it quickly gained recognition among mathematicians and scholars. Its clarity and thoroughness made it an essential resource. Pascal's framework provided a foundation upon which subsequent work in combinatorics, probability theory, and numerical analysis could be. That Pascal's work provided clarity meant that it was seen as a major contribution to mathematical science. It became an established resource. It also paved the way for progress. Pascal's discoveries had profound implications across mathematics and science, shaping the direction of research for generations. Its impact underscores the importance of Pascal's legacy. Section 13, Comparison to prior work on similar structures. While Pascal's on the arithmetical triangle presents the triangle's properties with unprecedented clarity and detail, it is important to acknowledge that precursors to this structure existed earlier in mathematical history. Mathematicians in India, China, and Europe had previously identified the numerical patterns and relationships embodied within what would come to be known as Pascal's triangle. However, it is in Pascal's work that the triangle receives its most systematic and rigorous treatment. That predecessors to Pascal exist reveals the complex nature of mathematical discovery. Innovation is not something that one individual can provide in isolation. Pascal's contribution provides a more thorough examination. Furthermore, Pascal frames his exploration of the triangle in the context of the problems of his time, and this makes it especially useful. It is this careful construction that underscores the enduring impact of his treatise. Section 14, Internal Consistency Checks within Pascal's treatise. Pascal demonstrates remarkable internal consistency throughout on the arithmetical triangle. All the various theorems, properties, and applications that he presents are logically connected and mutually reinforcing. This consistency lends credibility to his claims that its internal structure is cohesive solidifies the work's value. Pascal demonstrates a commitment to mathematical rigor. Pascal's ability to create a framework built on logic is a testament to his intellectual insight, the logical structure, and to its enduring value. Section 15, The Significance of Pascal's geometric approach. Pascal's treatise embraces a geometric style of presentation, utilizing visual representations and spatial reasoning to convey mathematical ideas. This approach is reflective of mathematical traditions of his time. Pascal's choice of geometric presentation suggests a deep connection between mathematics and geometry. Pascal's approach promotes an intuitive grasp of mathematical concepts. The geometric style connects the abstract properties of numbers to tangible spatial experiences. This combination makes the concepts easier to understand and appreciate. He combines visual thinking with analytical rigor. This combination makes this treatise uniquely accessible to a broad audience. Section 16, Pascal's treatment of infinite processes and limits. Although on the arithmetical triangle primarily deals with discrete quantities, Pascal's work contains the seeds of later developments in the area of infinite processes and limits. The properties of the triangle, when considered across an infinite number of rows and columns, hint at the potential to explore infinite sums and convergence, laying the conceptual groundwork for some future developments in calculus and analysis. Pascal's insight sets the stage for new explorations. This section highlights Pascal's visionary ability to see beyond the immediate scope of his work. He suggests the potential of his discoveries for addressing questions of infinite sums and limits. Pascal's vision expands the scope of his ideas. It is a pointer towards future developments in mathematics. Section 17 Influence on later mathematicians. Leibniz' combinatorial on the arithmetical triangle exerted a powerful influence on later mathematicians, including Gottfried Wilhelm Leibniz. Leibniz, who was deeply interested in combinatorics and the construction of a universal symbolic language, drew heavily from Pascal's work and ideas. Leibniz applied Pascal's findings to his own research. Pascal's influence on Leibniz demonstrates the far-reaching consequences of his inquiry. Pascal's work served as a source of inspiration for Leibniz. Leibniz expanded it and applied it to new problems of formal logic and computation. Leibniz highlights how Pascal was on the cutting edge. Section 18 The role of perfect induction in Pascal's proofs. Pascal's proofs and on the arithmetical triangle often rely on the principles of perfect induction. It is the method of showing something to be true for a base case and then proving that if it is true for some case then it must be true for the next case. Pascal shows how this strategy makes it possible to provide rigorous arguments. This focus underscores Pascal's commitment to mathematical rigor. Pascal is concerned with providing proofs that are not only true but that also demonstrate the underlying logic that governs the structure and properties of the arithmetical triangle. Pascal's work has a solid core. The proofs show the power of inductive reasoning as a strategy for mathematical verification. The core claims outlined by Pascal in his treatise on the arithmetical triangle exhibit a remarkable degree of accuracy, coherence, and significance. While Pascal may not have invented the triangle itself, his systematic exploration of its properties, his rigorous proofs, and his insightful applications to problems of combinatorics and probability solidify its place as a cornerstone of mathematical thought. The essay demonstrates that Pascal's claims are largely correct. His careful, rigorous, and thorough approach makes this work of value. Pascal's contributions endure due to their precision, the rigor of his arguments, and the profound implications his findings have for mathematics and science.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.